Hello students, welcome to the 17th lecture on particle physics, and today we are going to talk about charge conjugation operation. This charge conjugation is an internal symmetry unlike parity and time reversal, and this symmetry illustrates the symmetrical transformation between particles and their corresponding antiparticles. Now, when we are operating charge conjugation operation on particles, we are getting antiparticles. Then what are the different quantities, those changes under this operation? Then it changes lepton number, it changes baryon number, it changes charge, it changes magnetic moment because of the sign of the charge. What it does not changes energy, position of the particle, its momentum, etc. Therefore, this is what we are going to talk about. Simply speaking, this symmetry means that if physical laws predict the behavior of a set of particles, then they will predict exactly the same behavior for the corresponding set of antiparticles. Suppose, for example, if I am talking about a reaction A plus B going to C plus D, and at some set of mass energy, I have obtained the cross section for this reaction. And then we apply the charge conjugation operation, and we have A bar plus B bar going to C bar plus D bar. What it tells you that at this same center of mass energy, the value of the cross section will be exactly the same. Therefore, a collision between a muon and a proton will look exactly the same as the collision between an anti-muon and anti-proton. Charge conjugation operation, while replacing a particle with its antiparticle, does not change the position, energy, momentum, spin, and time. That is, the state of the system is unchanged. While the signs of all the additive quantum numbers like lepton number, baryon number, electric charge, magnetic moment, strangeness, charm, beauty, and truth, they change. For example, if I am operating charge conjugation on proton, then I am getting an anti-proton with some phase factor that we will talk about later in this course. Then baryon number for proton is +1, for anti-proton is -1. If I operate C on lambda, then we are getting lambda bar. Though lambda is a neutral particle, but the antiparticle of lambda is anti-lambda. Therefore, charge conjugation operation, when it's operating on lambda, it is changing to anti-lambda with some phase factor. Now, baryon number for the lepton is +1, for anti-lambda is -1. Strangeness for lambda is -1, while for anti-lambda is +1. That is why we are talking about the additive quantum numbers, they change, like strangeness, electric charge, etc. Now, since the charge and magnetic moment of every particle changes its sign, therefore the electromagnetic interaction remains invariant under this operation. That is, the Hamiltonian of the system describing an electromagnetic interaction commutes with the charge conjugation operation. And since we have discussed that the Hamiltonian of a given system commutes with an operator, then the quantum number associated with this operator is a conserved quantum number. Here, charge conjugation operator commutes with the Hamiltonian of an electromagnetic system, and therefore charge conjugation is a good quantum number or is a conserved quantity in the case of electromagnetic interaction. Similarly, that is true for the strong interaction process, while in the case of weak interaction, charge conjugation is not a good quantum number. That means the charge conjugation operator does not commute with the Hamiltonian of a system which is described by weak interaction. Now, since C changes particle to antiparticle, therefore C operating on a proton state results to antiproton state with this phase factor, and without changing its position, its momentum, and its spin. These are unchanged. And then when you repeat this process, you should get the original state. That means if you operate again by charge conjugation operation on antiproton, you will get a proton. Therefore, what you will have C square operating on P will result xi operating on C P bar from here, and then you are getting xi square P, and that should give us the original state, and therefore xi square should be 1, and that means xi should be either +1 or -1. Now, most of the particles in nature are not C eigenstate. For example, if you talk about proton and you operate by charge conjugation operator, then you are getting antiproton, and by this definition, you are getting as plus minus the proton state. Now, what does that imply? That proton and antiproton are representing the same physical state with a difference of a plus or a minus sign. Now, we know that that is not true. Proton and neutron, they are entirely two different worlds. Therefore, in general, they are not good eigenstates or of charge conjugation operator. Similarly, you can talk about electron, you can talk about any other particle. If we will have electron and positron, we know that antiparticle of electron is positron and the charge changes and all that. Therefore, they are not one and the same. Similarly, if charge conjugation operator operates on a neutron state, though that is charge neutral, it gives us an anti-neutron. Without changing its position, momentum or spin, this is a neutral particle. What is happening? That for neutron we have baryon number +1, while for anti-neutron baryon number is -1. Besides that, the magnetic moment for the neutron is -1.91 nuclear magneton. That is what we call by the name anomalous magnetic moment of the neutron, while for anti-neutron it is +1.91 nuclear magneton. Therefore, exactly in the same, they have the same magnitude of the magnetic moment. Now, the only particles which are their own antiparticles are definite eigenstate of C. As I have told you that C operating on P is equal to plus minus P or is equal to P bar, which is not possible. This can be true only for those particles which are their own antiparticles, like pi 0, like eta 0, like omega, like rho 0, etc., etc. Therefore, these are all neutral particles. They are all zero charge particle, and they are all mesons, as you can see here. And then you have photon. Then that means that fermionic states cannot be a good charge conjugation eigenstates. Bosonic, when we talk about bosonic states, then pi plus also cannot be a good eigenstate, because charge conjugation will give me pi minus, while by definition this should be plus minus pi plus. These two, pi minus and pi plus, are two different particles, and therefore this is not true for also charged mesons, but these are true for neutral mesons and photon, which are neutral in nature, and they can have eigenvalues +1 or -1. That means they can be even C-parity state or odd C-parity state. recall from the yesterday's lecture, we were talking about even parity and odd parity, where we were discussing about operation of spatial inversion. Here we are talking about C operation, charge conjugation operation, and here we are introducing C parity to be even or C parity to be odd. Therefore, what to conclude, that we have charge conjugation operation operating on proton is giving me a phase factor times it is giving me anti-proton, and repetition of this should give us return us the original state, implying that this xi should be +1 or -1, even parity or odd parity, and since C operating on P will give me P bar, or C operating on E minus will give me E plus with a phase factor. Therefore, these cannot be C eigenstates. What can be is a pi 0 or a photon. That means pi 0 is a good C eigenstate. That means the eigenvalue associated with the C operator that can be determined in the experiments, and that is what we can talk about. But before going to the particles, let us here also talk about what happens when C operates on electric field, magnetic field, what happens when C operates on the Maxwell's equations. As I have told you that electromagnetic interactions Hamiltonian is invariant under C operation, and we will see that Maxwell's equations are invariant under C operation. But before that, let us talk about the electric field, magnetic field, vector potential, scalar potential, etc. Now, what is electric field? The example we have seen that it is force per unit the test charge, and that is given by 1 by 4 pi epsilon naught q by r cube times r. Either you can write it as 1 by 4 pi epsilon naught q by r square unit vector r, or I am writing it as 1 by 4 pi epsilon naught q by r square r vector by mod of r, and these together I am writing it as r cube. Now what happens when we apply charge conjugation operation? As you see, r does not change while q changes to minus q. Therefore, what we are seeing, that electric field changes to minus E when we operate by charge conjugation operation. Now let us look at magnetic field. Now magnetic field, recall the Boyd-Stewart law which we have discussed in parity. I is dq by dt, and when we are talking, and the other quantities are related to a space coordinate. Therefore, C is going to act on Q, and it will change dq by dt to minus dq by dt. Electron is flowing the direction of the current, and the positron is flowing in the direction of current. They are opposite, and that we are realizing by looking at I changing to minus I. This implies that B is changing to minus B. While recall, parity operation, when we operate parity operator on the electric field changes sign while magnetic field does not. But here both the electric field and magnetic field, they are changing sign. Now look at the definition of electric field in terms of the scalar and vector potentials. We see that this is del, that depends upon spatial coordinates. This is not going to change under charge conjugation operation. This is the scalar potential defined by this guy. Q is changing to minus Q. E is changing to minus E. And that means A is changing to minus A. And therefore you can look at here also, B is changing to minus B, delta is unchanged, and A is changing to minus A. Therefore, both vector potential and scalar potential, they change sign under the C operation. Now with this, let us talk about the Maxwell's equation. As you can see that divergence of E is rho by epsilon naught. E changes sign, rho changes sign, and this is unchanged. Now here del does not change sign, E changes sign, B changes sign, T does not change sign, and therefore this is invariant. And similarly you can work out for these two, they are very trivial. Okay, Gauss's law in magnetostatics, and the fourth one, which is, you can see that del is not changing and B is changing to minus B, J is changing to minus B, J, and D is changing to displacement current is changing to minus D. Now let us try to understand the how we determine the C parity of photon. As I have told you, we can determine the C parity of photon, pi 0, omega 0, eta 0, etc., etc. And let us start with the C parity of photons. Now what we have discussed while talking about the parity operation and determining the parity of photons, that the vector potential A corresponds to the photon wave function, and the wave function for a photon with momentum k propagating freely through space is given by this expression. Now n is the normalization constant, epsilon is the polarization vector, and this is exponential of a dimensionless quantity which is a scalar. Therefore we will forget about it. Then this is normalization constant. If A is changing to minus A, that means epsilon has changed to minus epsilon, and that means C parity of photon, as we have seen phi changing to minus phi and A changing to minus phi, C parity of photon is odd. Therefore we have to be clear that the photons have odd parity as well as they have odd C parity. Now let us talk about neutral pion. Now what we have discussed while talking about parity, that neutral pions decay to 2 photons. It does not decay to a single photon, and it also does not decay to 3 photons. This does not take place because of energy momentum conservation, and this has been observed. Predominantly a pi 0 decays to 2 photons. It is not observed while it conserves energy and momentum. This is because of the C parity. As you can see that when I am talking about pi 0 decaying to 2 photons, photons have odd parity, C parity. Therefore overall for the 2 photons the C parity will be even. For the 3 protons C parity will be odd. And that means we are talking about photons in the final state. That means we are discussing electromagnetic interaction. And in electromagnetic interaction, C is a good quantum number. And therefore, what we are finding out that in the second case, C parity of pi 0 is even, while in the third case it is odd. Both cannot be true. What has been observed that pi 0 decays to 2 photons. And because of the non-conservation of C in the third case, it is odd. This is not observed in the laboratories. So it has been observed that pi 0 does not decay into a single photon or 3 photons. The first one is because of the energy momentum relation, because we can talk about the rest frame of photon, and then this will be the mass of the photon and the rest frame. Photons are massless, therefore you have zero energy in the initial state, while in the final state at least you know you have to have the existence of pi 0, and existence of pi 0 means there should be rest mass of the pi 0, and that means at least you need 135 MeV of energy. From 0 you cannot get 135. That is why from the energy evaluation this is not allowed, while what I am talking about, when you have 3 photons, the C parity will turn out to be -1, while for 2 photons it will turn out to be +1. Since in electromagnetic interaction C is a good quantum number, therefore it has been observed that C pi 0 decays to 2 photons but not to 3 photons. As experimentally, the latest data tells us that the branching ratio for pi 0 to 3 photons upon the total branching ratio include all the possible processes, this is less than 10 power minus 8. And for eta 0, because eta 0 also does not decay into single photon, it decays into 2 photons, it does not decay into 3 photons. Here the present experimental limit is that this possibility is 10 power 5 times smaller than the all decay rates. Therefore, the reason for pi 0 and eta 0 to not decay into 3 photons is because of the C parity. That C parity is getting violated in this one when we go from this to this. So either we could have this process or we could have this process. This has been experimentally observed and we are not observing it. And there are current experimental limits on pi zeros or eta zeros going to 3 photons in the final state. Then this is also the reason for omega 0 to decay into a pi 0 and a photon and not decaying into pi 0 and 2 photons. Again, see, I'm taking an example of electromagnetic interaction because we have photons in the final state, and as we have seen that the parity of C parity of pi 0 is even, photon is odd. Photon is, we have seen, look at it. C parity of photon is odd. C parity of pi 0 is even. And therefore, when we are talking about omega 0, this is odd and even, that means this is odd, while here we have 2 photons and this will make this to be even. Therefore, we cannot have both the possibilities. We have observed this, but we haven't observed the other process. Therefore, omega 0 is decaying into pi 0 to single gamma, but omega 0 is not decaying into pi 0 and 2 photons in the final stage. And therefore, we say that C parity of omega 0 is -1. As you can see that this is +1 and this is a multiplicative quantum number. Therefore, +1 and photon is -1. We are getting -1. While here it will be +1 times -1 times -1, and that will be +1. Therefore, here it is even C parity state, while here it is odd C parity state. Both cannot be true, and this has been observed. Now let us talk more about C parity of fermion and anti-fermion bond state. For example, if you take quark anti-quark state, or you take positronium system. Positronium is an electron-positron bound system. Or you can take quarkonium system, QQ bar, like CC bar system, BB bar system, etc. Charmonium system, and the BB bar system is known as the botonium system. Now we can determine the C parity of these, you may call broadly as atomic systems, whether you are talking about positronium system or quarkonium system, or you are talking about pi plus, pi minus, or pi 0, where you have quark and anti-quark. Now, when we are talking about quark and anti-quark, and we are talking about charge conjugation operation, we know that when we will apply C to U bar, it will become U, and U will become U bar, and that will be equivalent to U minus U bar, and this is corresponds to a mirror reflection. And this is a bond system. We have seen that the orbital parity is given by minus 1 to the power L. Then we are talking about fermions, and fermions are described by, these spins are described the anti-symmetric wave function, and the symmetry of the wave function is taken care by a factor of minus 1 to the power s plus 1. Then quantum field theory desires that if you are changing fermion to anti-fermion, you should pick up a minus sign that we will talk about when we will discuss the Dirac equation and other things, that interchanging fermion to anti-fermion, one picks up a minus sign. Therefore, under charge conjugation operation, the overall sign for such type of FF bar system, one is fermion and another is for anti-fermion, is L plus S plus 1 coming from this part. This is even. That means overall there is a sign of minus 1 to the power L plus S when we are talking about a bound system. Therefore, overall the change in sign in a bound system is minus 1 to the power L. L corresponds to the atomic state that we are talking about, whether it is S state or P state or D state, etc. And S is the total spin. Now, when we talk about C-parity of positronium system, then what is a positronium system? This is a positron, this is an electron revolving around it, and then we say that the Coulombic potential will be 1 by 4 pi epsilon naught minus E square by R, because it will be attractive in nature. We are replacing positron by proton by positron. Proton was there in the case of hydrogen atom. Positron is here in the case of a positronium system. And negative sign is telling us that this is a bound state. Now, if you recall, in the case of hydrogen atom, this energy was 13.6 by n square, where the reduced mass of the system by when we solve Schrodinger equation, this was actually given by m1 m2 by m1 plus m2. That means this is me mp by me plus mp. But since mass of proton is 1836 times more than mass of electron, therefore we drop this and mp and mp cancels out. Therefore, approximately reduced mass is taken to be the same as mass of the electron. And we get a value of, while solving Schrodinger equation for third hydrogen atom problem, to be minus 13.6 by n square. While here the reduced mass is me electron, me positron by me plus, and mass of electron is the same as mass of positron. Therefore, we are getting a factor of me by 2, and that factor is getting reflected here. Therefore, we have the energy as minus 13.6 electron volt upon twice n square. Now, the 3s1 state with principal quantum number 1 is called the orthopositronium state, and the 1s0 state is called the parapositronium state. And we will talk about these states in our next class, and how one can determine the parity of positronium system, and then we will extend this to the charmonium and botonium system. Let's stop here. Thank you very much.